only this part. Which part? Quarter wave length alone. In this part it is a big question. Single step and double step, if they are asking the theory question, it is also a 13-mark question. Okay, application of Smith chart, and Smith chart is also a 13. See, some people, they don't ask the Smith chart itself. Some people, one question from the Smith chart, one question from the other part. Okay, so based upon the people who are taking this one, you have to write. So if you know now itself in this part, if you understand what do you mean by input impedance, what do you mean by standing wave ratio, this admittance, everything only, then when we are plotting the Smith chart, it will be easy for you to understand. Are you able to follow? So first thing you have to understand in the theory part, then only the problem will be easy. So based on formulas, we will be substituting the Smith chart. The thing is, we will be calculating all the values: standing wave ratio, voltage standing wave ratio, input impedance, admittance, everything. We will be calculating the reflection losses, everything in terms of the Smith chart. Also, we can do the calculations. Are you able to follow? Yes or no? The concept, if you understand, means, see, TLRF paper, they always say it's a tough paper, but thing is, if you understand the concept of this, it is very, very easy. But if you don't understand the concept and if you memorize means, the subject will be a tough subject. So that's what I am saying. Listen to the class, take the notes properly and study it in the class itself. Then if we go through during the exam timings, it will be easy. Because after the first internal test, after 9th only, the 14th I think, something only the third internal cycle test starts. That means this topics again, the second week of August only you are going to learn for your test. Right? The first 2 units also very easy. If you have listened to the class and understood and if you study. Okay. So now you put the heading quarter wave length impedance matching. So first thing you note down, what is the first step? What you have to write? The generalized expression for input impedance. Note down. The generalized, everything the step is same. The generalized expression for input impedance of the line is given by, just write a formula, Z is equal to R naught, Z R plus J R naught, tan beta S R naught, remove your mask, J is R tan beta S. This is equation number 1. So if you are directly substituting the lambda by 4, the value means the value will go to 0 or infinity. So we have to rearrange this equation by dividing this equation by tan beta S. Note, dividing equation 1 by tan beta S. Dividing equation 1 by tan beta S. Divided the equation fully you have to divide by tan beta S. So ZR by tan beta S plus J R naught, because tan beta S by tan beta S it will get cancelled by R naught by tan beta S plus J Z R. After this we have to substitute like usual way, theta is equal to 2 pi by lambda is equal to what? So S is equal to what? Lambda by 4. For quarter wavelength, for quarter wavelength, S is equal to lambda by 4. Substitute lambda by 4 in this equation. Zn is equal to R naught ZR tan 2 pi by lambda into lambda by 4. In the place of S, I am substituting as lambda by 4 plus J R naught divided by R naught by tan 2 pi by lambda into lambda by 4 plus J ZR. Cancel the equations. I do the simplification and see what is the value you are getting in degree mode for that term value. When you do the simplification, what you get? Zn is equal to R naught ZR by tan pi by 2 plus J R naught by R naught tan pi by 2 plus J Z R. What is tan pi by 2? Infinity, right? Tan in degree mode, infinity. So this terms will go off, right? So it will be getting as Zn is equal to R naught J R naught by J ZR. J terms will get cancelled. So your Zn is equal to R naught square by ZR. This equation already this you can note out this equation itself as 2 and then we can put this as 4. This equation is similar. I will return. See, input impedance you are taking, just we are rearranging, otherwise in the beginning stage itself if we substitute, it will go to infinity, entire term will get cancelled. So we are rearranging the equation and after that we are substituting beta value and S values and we are getting over this equation. Note down. Thus equation 4 is similar to the equation. Thus equation 4 is similar to the equation for impedance matching using transformer. Thus equation number 4 is similar to the equations for impedance matching using transformer. For impedance matching using transformer. Thus the quarter waveline may be used as a transformer. Thus the quarter waveline may be used as a transformer for impedance matching of load Zr with input impedance. Thus the quarter waveline may be used as a transformer for impedance matching of load Zr with input impedance. Zin is equal to Z in is equal to ZR. The input impedance Z in is equal to ZR. Next note down. For matching impedances, ZR and Zin, for matching impedances, ZR and Zin, the line with characteristic impedance are not. For matching impedances, ZR and Zin, the line with characteristic impedance are not, may be selected such that the condition given below gets satisfied. R naught is equal to modulus of root of ZR plus ZA. R naught characteristic impedance is equal to root of ZR into ZA. We write it as equation number 5. For matched impedance Z in with ZR, what condition for the characteristic impedance should be satisfied? R naught should be equal to modulus of ZR into Z in for matched impedance. Underline the words. See, underline the words. Quarter line may be used for the transformer for impedance matching. Underline the words. Quarter line may be used as a transformer for impedance matching. You underline that word. And then for impedance matching of ZR and ZA, that condition also, what is the condition you have to note down. Next one you note down. A quarter wave line can transform a low impedance. A quarter wave line can transform a low impedance into high impedance and vice versa. A quarter wave line can transform a low impedance into high impedance and vice versa. Thus it can be considered as an impedance inverter. Underline the word impedance inverter. Consider also underline. Considered as an impedance inverter. Hence an open circuited lambda by 4 line. Hence an open circuited lambda by 4 line gives zero input impedance. While a short circuited lambda by 4 line gives infinite input impedance. Open circuited lambda by 4 gives a zero input impedance, while a short circuited lambda by 4 line gives infinite input impedance. Thus, a short circuit quarter wave line behaves as an open circuit. Thus, a short circuit quarter wave line behaves as an open circuit. At the other end, while the open circuit quarter wave line, while an open circuit quarter wave line behaves as a short circuit, thus a short circuit quarter wave line behaves as an open circuit at the other end, while the open circuit quarter wave line behaves as a short circuit at the other end. Behaves as a short circuit at the other end. Okay. The next one, the quarter wave. Next paragraph. See, next paragraph you note on this. The quarter wave matching section. The quarter wave matching section has number of applications. The quarter wave matching section has number of applications. Under the application you put the first point. The quarter wave transformer has got number of application. Under that, the first application. One of the important application is the impedance transformation. One of the important application is the impedance transformation in coupling a transmission line, in coupling, C-O-U-P-L-I-N-G, coupling a transmission line to a resistive load. One of the important application is the impedance transformation in coupling a transmission line to a resistive load. Impedance transformation in coupling a transmission line to a resistive load such as antenna. Resistive load such as an antenna.